Thanks for coming here this evening. I'm going to start with a question. Who in the past few days, or maybe a week or so, has heard about gravitational waves? I knew it. Almost everybody. Well, I'm very happy that about a year ago we chose this date for our event, given our complicated schedules. And I'm very happy that this date was chosen because it happened to be, of course I didn't know at the time, but it happened to be about 10 days after a big announcement from the collaboration that I'm a member of. And I'm very happy to be able to tell you all about it, even though you read about it in the New York Times, and New Yorker, and Chicago Tribune, and all the newspapers. Okay, so let me see if I can get this. All right, so I'm going to start from the beginning. I'm going to go back to what Wendy was talking about and give you a sense of why this new discovery is kind of important. So what we all do, what we're all trying to do is to probe the universe. We're trying to poke at it in many different ways and figure out why it behaves the way it behaves. So the way we probe the universe is, of course, using telescopes. And let me ask you, what do you think was the very first telescope ever used by humans? By the way, my accent is Greek, so where is our host? I was very happy to hear that you just visited Greek. So what were my ancestors using? Any guess? The eye. People are pointing to their faces. It's the eye. And we learned as much as we could through the eye. But really, modern astronomy started with Galileo about 4 centuries ago, who took a little tiny tube with glass on both sides, turned it towards the sky, and started what is now modern astronomy. What I'm about to tell you is basically a moment in our history as astronomers where we're doing almost the same thing as Galileo did 400 years ago. I'll explain why. Now, over the centuries, for 3 centuries, we were observing the universe with our optical telescopes. Wendy is still doing it with amazing optical telescopes now. But in the previous century, we had an amazing epoch of telescope innovation and cosmic exploration. And we have built some of the royal we, as astronomers, the community, has built amazing telescopes at tops of mountains. We observe now the universe not just in optical light, but it also in radio waves. We have been to space. We observe it in X-rays and gamma rays, and of course also in particles that Angela is touching or smelling. We'll talk about this over dinner, which is more relevant. But what happened, so this is our previous century. We have discovered amazing things that we were not expecting. But this year, well, kind of last year, on September 14, 2015, my life changed because for the first time ever, we basically detected binary black holes that you can see here in the movie, and we detected gravitational waves emitted from binary black holes. And we opened essentially a new era of astronomy. Now, gravitational waves are waves, disturbances, but they're not like electromagnetic waves. Instead, they are waves that disturb the space around very massive objects. And gravitational waves were a prediction made by Einstein exactly 100 years ago, based on his theory of general relativity about how gravity works. And his idea was that any mass, especially massive objects, disturb the space around them. They warp the space and create little wells, little dimples in flat space. And the motion of every object is actually governed by how the space is warped, and they're following basically the curvature of the space, and that's how you have motion of cosmic objects in the universe. Now, if you have these dimples and your objects are moving, then what you get actually is a disturbance that propagates, gets generated and propagates from the source out to large distances. It's a disturbance, a wave of the space itself. It's actually of the space-time, but it's easier for us to think in terms of space. So these oscillations of the fabric of space is what we are observing with a new type of telescope. And these are the gravitational waves that are coming from, now we know, a pair of black holes. Black holes are dead bodies. They are the remnants of very massive stars. When stars consume their nuclear fuel and they have no more fuel to burn, they collapse under their own gravity, and they form these extremely compact masses that disturb space enormously. So if you're close to a black hole, we're going to see now a little movie of what happens when two black holes find themselves in orbit one around the other. They disturb the space. You see the two, wells, and as they're moving, their disturbances are propagated in terms of waves. This down here is actually a general relativity model of the signal that fits the data amazingly well. And this is the kind of wave that we measured with our new gravitational wave telescopes in quads. So the black holes are losing energy in the waves. They're coming closer and closer together. The amplitude of the signal goes up. You can see how the height here goes up as they're coming closer together. Eventually, the two black holes touch, and they merge into one bigger black hole in a burst of gravitational waves propagating from the source and reaching our detectors. This is what we observe. This is not just an artist's impression. This is an actual scientific simulation following the properties of these two black holes. And the black holes were of about 30 times the mass of the sun, and eventually they formed something that is about 60 times the mass of the sun. Now, earlier, my friend said, I listen to the universe. Why do we say this with gravitational waves? Well, there are two reasons. One is that the frequency of this oscillation caused by the binary black holes is very much in the same range of the sound wave frequencies that our ear can hear. So we can take a gravitational wave, transform it into sound. It's not sound, okay? Gravitational waves are not sound waves, but the frequencies are very similar. You can transform it into sound and actually listen to them. The second reason we say that is that our detector works a little bit like our ear. Telescopes like Wendy's telescopes, for example, are pointing instruments, like our eyes. I can look light coming from your direction, but I cannot see light coming behind me. But my ears can hear sounds from all around me. And in that sense, gravitational waves and gravitational wave detectors act like sound. So we're going to now hear not just some simulation of gravitational waves. We're going to hear the actual signal we detected on September 14, and we announced publicly 10 days ago. So let's see if this is going to work with the sound. So I'm going to go back and try to explain, and then we're going to listen again. The sound you heard is actually quite noisy. That's the noise we have in our detectors, okay? No detector is perfect. You don't just get signal, but you actually get Earth detector-generated noise along with your signal. The actual gravitational wave is this chirp-like sound that is audible better in the second run, which is going like whoop, whoop, and it's very short. And it's very short because these black holes specifically that we observed for the first time ever are very massive, and their signal is very short. It's only 1/5 of a second in our data. The other thing you will see, so the signal you're going to see is the color bananas. These are the two detectors we have. Color bananas shows how loud the signal is, and the fact that it's going up in frequency, which is tells you that the black holes are coming closer and closer to one another. So if we listen to it again. So the second time you hear it better. The first time is the actual frequency of the gravitational wave. The second time we artificially shifted to a little higher frequency that our ear is more sensitive. And you can hear the whoop much better. okay? So these are the sounds, the signatures of merging black holes in the universe. It's the first time we have observational evidence that binary black holes actually exist and they merge into bigger black holes. These black holes that you're looking at are actually moving by the end of their lives, before the merger, they're moving at half the speed of light. Nothing we have seen as directly as this in the universe we've ever caught it moving at this kind of speed. So we're testing the theory of gravity at these extreme environments very close to the black holes. Okay. Now let me tell you a little bit about this particular source we observed. One couple of slides. So this merger of the black holes happened 1.3 billion years ago, before multicell life had developed on the Earth. It started its trip and traveled across many, 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 many galaxies until it reached our detectors on September 14. When the merger happened, the black holes released an enormous amount of energy in a very short amount of time. At that time, Wendy, the source outshone by a factor of 50 all the stars, the 100 billion stars in all the galaxies, the 100 billion galaxies in the known universe. It's the most powerful, brightest source we have ever seen in any kind of signal from the universe. It produced 3 million times the energy needed to destroy the sun. The final black hole is 200 miles across. It fits within the state of Illinois from Indiana to Missouri. And the way we observe these is with very weird telescopes that I won't have time to explain, but we are able to measure changes in space, disturbances, as small as a single atom diameter in the whole distance of the Earth, from the Earth to the sun. This is the most precise measurement we've ever made as humans. I can answer maybe what this small measurement really means. It's a tiny, tiny little disturbance in space. And I want to end by emphasizing, actually we didn't coordinate on this, but it's our reality. LIGO and the other instruments are all about people. I'm a member of this collaboration. The collaboration has 16 countries, more than 1,000 people. We have telecons at weird times, and we communicate a lot over email. Within the collaboration, I've been for 15 years. It's been a long way coming, this discovery. And I have led the astrophysical interpretation of the source. So we're very proud to have opened gravitational wave astronomy for all of us, and especially for the younger generation, a new way of looking at the universe.